I'm a postdoctoral researcher, so I guess I'm speaking mostly to undergraduates here, but to make sure everyone's familiar with the various positions within academia. Obviously, undergraduate's kind of where you start seeing the base of the lab present with people doing research at undergraduate level, which we're talking about today. And then past that, graduate school, PhDs, working in physics and research. Once you get your PhD, you generally go, well, there's a lot of different career paths you can do at that point. What's considered the academic track is what I'm doing, which is a postdoctoral position at a lab or a research group, typically a few years at a time. You can do several of those. And then if you continue academic track, you can go on to being a professor, which is actually what I'm applying for this year. Actually, I've been applying for professorship positions. So that's kind of the general arc. Of course, there's many places there you can branch off into, industry, other research positions, national labs, NASA, Department of Energy. A lot of different options, or even within universities, there's often research-specific positions, what I'd call a research associate or some position similar to that. Anyway, so that gets to what I'm doing. Is I'm a researcher here at UCSD. I work in Professor Brian Keating's lab. I also work very closely with Professor Cam Arnold, who will be joining us later. And often how that works is the faculty, the professors organize the larger scope of a lab, all the research activities and that sort of thing. Postdocs often come on to really organize and implement a more specific part of that. So that's my background image here. This is one of our telescopes, a CMB telescope that is in a lab at UCSD right now that we've been working on. So I came in to design, build, and test this over the last 4 years now almost. And that has happened with the help of a large amount of graduate researchers as well as undergraduate researchers, which I'll tell you a little bit about. But given that this is physics, building the experiment and getting it working is a lot of fun, but only if there's an exciting, motivating research behind that. So I'm going to start out just telling you a little bit about what motivates the research we do here at UCSD. That's what the CMB, the cosmic microwave background. So that's this first image I'm showing you is that classic image of the glowing ember of the Big Bang, the cosmic microwave background. And let's see here. So, and I should say that these are the telescopes that I'm predominantly working on right now with something called the Simons Observatory, which is a specific CMB observatory, although there are a number of them. With this being a 6-meter class telescope. You can see these little things are doors here. There we go. That's a door there. And then this is like a garage-sized door here, but these are these array of 3 telescopes. And right in the middle there, which you can't really see because it's too small on this scale, is will be the camera that's behind me. I'll talk a little bit more about that too. Let's see, I should also say there aren't, this is a fairly small group of people. So if you have questions or, want to, don't understand something or curious about something, feel free to either raise your hand or raise it on the chat or some other method of letting your question be known. All right, so this gets into kind of what we're looking at specifically with our research. Is here we are up at the present universe. This is this very common, I call the Bell diagram of the history of the universe, where you're looking more distance, you're looking more back, farther back in time, growth of all structure in the universe, and you have this dark age period before you get the first stars and galaxies, and right before that is the Big Bang and this afterglow pattern called the cosmic microwave background. So this is about 13-something billion years ago. The cosmic microwave background is about 380,000 years after the Big Bang. Effectively what it is immediately after the Big Bang, the universe is this hot plasma that's expanding and slowly cooling. And once it gets cool enough for electrons to combine with nuclei to create hydrogen and helium, neutral hydrogen and helium, light is able to travel out through the universe and reach us. So we're able to look at this pattern that's relatively soon after the Big Bang, and by really looking closely at the statistical properties of that surface, we can really tightly constrain the kind of fundamental properties of the universe. And if you ever heard of lambda CDM, the cold dark matter universe, the kind of dominant theory and parameters thereof of how we think our universe it operates and evolves, a lot of the tightest constraints on that is from CMB science. And in fact, it's a rich field and a fairly recent field. So this is first observed in the 60s. So it's only been about 60 years we've been looking at this. It's come a long way in 60 years, although we've still got some things to do, which I'll tell you a little bit about. But let's see here. I feel the Big Bang is kind of seen as this, oh, of course, the Big Bang. But really 60 years ago, there was a number of dominant theories about how the universe formed and evolved. And it was only with observations of the CMB that the Big Bang theory really moved into a dominant position in that. But there's still a lot of things I know. I'm actually calling out inflation here because that's specifically what we're looking for. This is looking at the first fractions of a second after the Big Bang and really trying to understand what happened in that very earliest period. Just by some potential patterns that process could have imprinted on the surface. So that's what we're going after. That's the big, the big picture goals that really excite us and cause us to, or me, I guess I can speak to myself, it causes myself to devote a big part of my life to trying to understand that. Let's see here. I always like showing this because a couple things. This is our site in Chile. The Simons Array is an array of these 3 telescopes that a large number of people have worked on at UCSD. The first one has been there for, 5-6 years now, or perhaps a little bit longer. That was called Polar Bear. It was expanded into the Simons Array with the addition of 2 new telescopes and 3 new cameras. And a lot of the research we do in our lab is associated with the cameras that go in these telescopes. So I'll talk a little bit about that. Let's see here. I haven't worked on this as much, but I have actually been here. This is down in northern part of Chile. I was there to test some equipment with that first camera, 2017, I think, a few years back. And since then, we've had a lot of our graduate students going to the site this last year before the crisis hit to actually upgrade these camera systems. And so there's been a lot of recent work at the site and a lot of work in the lab getting ready for that. I'm pointing out the sky with microwave eyes because the CMB and what you do in the microwave isn't necessarily well understood, but just from, if you're not used to looking at it, but effectively, the cosmic microwave background is this incredibly uniform, about 3 Kelvin black body across the entire sky. So if you're actually able to see it, it would just look incredibly uniform to high precision. So I did want to point out with our science that we look at the delta T. We actually look at the fluctuations. If you ever see these maps of the orange and blue patterns, those are looking at these temperature fluctuations. And it's the scale of those fluctuations, how large they are in temperature, but also in polarized light, that can really tell us a lot of information about the structure of our universe. So that's a kind of exciting thing to look at. Moving off of that, the lab I work on and most, I would say, instrumentation labs is obviously heavy on the experimental side, the very hands-on side of actually designing and building these telescopes. So this is what we've been doing a lot of in the lab for the last few years, and that involves both graduate and undergraduate research projects associated with it. So I wanted to show this to give you a little bit idea of anatomy of a modern CMB telescope. And I would say this translates fairly well to a lot of different telescope types. There are usually some sort of re-imaging optics that can be reflective or refractive. For us, we have actually we use silicon lenses for microwave. This is a few meters on each side. Again, you can actually see it behind me. And for a lot of modern telescopes and a lot of modern physics experiments generally, you get better sensitivity by reducing thermal noise, and you do that by cooling down your camera or device. So we actually use what's called a dilution refrigerator, which is a really cool physics device in and of itself. That is a commercial device. We can buy one of these, and it allows us to cool down. It can reach base temperatures below 10 millikelvin, though we typically operate our focal plane, the actual place where our detectors reside, at 100 millikelvin. But this whole volume here is at 1 Kelvin, and this purple shell is 4 Kelvin. Green shell at 40 Kelvin, and then there's that red outer vacuum shell, which we've actually painted white, as you can see behind me, that allows us to cool down this far by removing all the air in here. Another interesting thing, as I mentioned, the polarized light signal is something we're really interested in looking at, and it's a challenging thing to observe correctly. And one of the ways we help improve our sensitivity to that polarized signal is by modulating it on the input. We do that by an actual physical optical device that rotates. So it's called a half-wave plate. It's a birefringent material that rotates the polarization state. And that sits at 40 Kelvin. And I mentioned this specifically because there was an undergraduate who did a senior thesis project on this that I'll mention, and is actually now continuing to work with the Simons Observatory half-wave plate that we've recently installed. What is it? I'll talk a little bit more about the details of it later, but it's a really cool device that we get to work with. Focal plane, let's see here. This is kind of an idea of the larger picture here. So this is also showing a lot of what I do is computer-aided design to actually get all these up and running in what we call SolidWorks is the program we use. We also have undergraduates that work with a lot of these design software, including some of these tanks and that sort of thing, the configuration. The camera wouldn't be much good if I couldn't point it on the sky where I wanted to, so there's a pointing platform that we also predominantly designed by a company in Germany, but it's something we work a lot with as far as components that integrate into it and making sure everything fits together properly. There's the camera there. This is a bunch of effectively shielding to control the illumination of the telescope. And then we actually have an array of 3 of these because the signal we're going after is very faint, so we need more than one telescope. This is always a fun thing to do in the research in our lab. A lot of it is design and build, and so this is something we've designed, and it's always fun when the thing you build actually looks like the design, so it's kind of satisfying. Give it a little bit more context. So I showed you that picture of the Simons array over here. There's actually 2 other CMB telescopes on the same plateau up in the Atacama Desert in Chile. This area is already being developed for Simons Observatory, so this has changed since this picture was taken, but we're up in the north of Chile. Let's see here. And water vapor is a hard thing for us, so we all of our equipment and all of our designs need to be rated for high altitude because this is the 3rd highest observatory in the world, up at 17,000 feet. So that's another kind of interesting aspect of the experiment. Anyway, so getting back to a little more down to earth here, talking about what it looks like in the lab. So this is a team, me and some graduate students and a postdoc. If you're not familiar with the term postdoc, that means postbaccalaureate. That means you've graduated from your undergraduate institution and decided to go work in a lab immediately. And we love it when that happens. And as usually happens if we have an undergraduate researcher who's a senior who graduates and has some time, either summer or a year or something, to finish up or continue work on some of the research projects they do. So actually we had 2 postbacks in our lab this last year. 3 actually, now I think about it. That's Chris right there. And this is another one, Joseph, who both worked in the lab as undergraduates and then went on to continue working at it after they graduated. But this more speaks to our day-to-day. It's assembly and goofing around a little bit, putting parts together. This is actually a collaborator from Berkeley. This is one of our graduate students working with another collaborator from Berkeley, assembling electronics, testing electronics, integrating them into the camera. And then this final one is actually testing the camera, where Chris there is below the camera. Testing all the electronics, testing the performance of the system, a lot of iteration on those as we add more components and understand things that work or things that don't work. I like showing this picture. This kind of just shows what the inside of the camera looks like. Again, this is the part that cools it. Just recently in March, we put in the first test pixel, so we're actually getting fairly advanced system here. We're actually able to test the full electronics system that allows us to convert light into a digital signal. That's a whole other interesting complex system that we work a lot with. To give you an idea of what our lab looks like, so I already showed some pictures from in the lab, but here's a graduate student hanging out at one of our desks. Not all of our labs have this much high clearance, but they are similar in concept: computing, electronics racks, different pieces of hardware that people are working on and getting ready to install on the camera or test externally. And that's the camera itself hanging out. Just to give an idea of things we often task undergraduates with, if we have a new person in our lab, a lot of the intro is getting familiar with the software we use. So computer-aided design with SolidWorks, it's getting up and running on how to do that, and often small projects, designing. A lot of what we use are custom parts. So designing custom parts, getting them made, finding out how to order that, how to specify it correctly. And then also in electronics design, we use a lot of custom electronics. This goes into PCB design and assembly. So once you actually order the electronics or physical pieces, putting that together and checking that it works properly and meets our needs. And then working with integrating that into the rest of the observatories. We do a lot of coding as well. Once you have a piece of test equipment, you need to actually implement it and integrate it with the overall software suite that we use to process our data. And then I also want to point out that we're not just experiment and instrument focused. We do want all of our researchers to keep an eye on the bigger picture. And so we have pretty frequent journal clubs where undergraduate researchers and graduate students and so forth have a place to practice presenting ideas, presenting their work, as well as presenting recent scientific papers or similar. Let's see here. I did want to I'll show a little bit more of this after I'm done going through the presentation. So let's see here. So I did want to highlight a couple people that work in our lab that were undergraduates at UCSD who ended up doing a lot of work in our house. So Chris Ellis, he's been great. He's been working with us for, I think, a little over a year now. Here's him. He's actually installing one of the decals on the telescope, but he's done a lot of work in helping us put this together, testing, say, the thermometry systems, understand how, when you cool something like this down to 100 mil-Kelvin, you want to know you cooled it down that far and how that whole system works. So he's done a lot of work with that. I show this picture again because that's actually Chris underneath the telescope, helping one of our graduate students with electronics tests of that thermometry system, but also helping with some of the other tests we do with the detectors and readout systems. I think he joined our lab as a senior after working with that graduate student as a TA. The graduate student was a TA he got to know through electronics course that was taught by Professor Cam Arnold. So that's a little bit about his story. He, I think, came to work with us as a senior to get some lab experience, and then stayed on as a postbaccalaureate researcher for a year. He's been with us for about a year now, basically doing a ton of work, and he's actually done a lot of work on systems we're deploying to Chile. So it's not just small items, these are fairly significant contributions that will go to Chile, will be an integral part of the telescope's operation. So he's done a lot of great things, and then he ended up applying for graduate school this last fall and is headed off to University of Reno to, I think, do graduate school in plasma physics or something similar. So that's been really great. We're going to miss him. And then another example is Bryce. Bryce is I don't actually know when he joined the lab, but it was a couple years ago, and he ended up working on the Siemens array cameras initially. on what we call the halfway plate, that polarization modulation device. And he ended up getting far enough along to write a senior thesis on it, which I think went quite well. And then he actually applied to grad school, decided to come to grad school here. And, oh, my microphone's a little funky. Can you guys hear me? I wonder if it was
Yes.
leaning back in my chair. Bad habits. So I think Bryce joined a couple years ago. Yeah, did a senior thesis, graduated, and is coming to grad school and continuing to work with our lab, which is fantastic for us because we're installing a very similar device into the camera right now. And I just wanted to show you some pictures of what he's been working on. Actually, recently he's been working on this. So we installed this device. It's there we go. It's this device spins, and it's really cool if you've ever seen those superconducting kind of magnetic levitation demos. This is applied. It uses superconducting ceramic pucks along with a magnet to provide a superconducting levitated magnetic bearing. And so it effectively traps the optical device. And this whole thing will spin at 2 hertz, which is a really sizable device to spin that quickly in a vacuum at about 40 Kelvin. That, of course, is no easy feat. So there's a lot of associated electronics with that encoding that Bryce has been working on previously and is working on right now. So this is just to give an idea that that's, the very basic checking if it were spinning. This is evidence of spinning at 2 hertz. Inside this, if you can't see it, this is this big overview of our lab space again, but now it looks a lot busier because you have this electronics rack, and that's another one actually. As long as vacuum equipment, all these hoses running every which way, busy lab bench. And this is an electronics box which actually runs this halfway plate, which Bryce has been doing a lot of work on the previous experiment, but also in this experiment to debug and kind of improve it. That's why it looks a little bit chaotic in this picture, is because we've been tearing it apart to fix various components and test some of the electronics and electronics boards that have been working. So he's been doing a lot of debugging work lately. So that was kind of a quick overview of that. I did want to exit out of that. Let's see, hopefully, can you guys still see my screen?
Yes, we can. Thank you.
All right, so you should be able to see this pressure. This is not a real pressure. That's because I unplugged that device, but I wanted to show this because this is actually live streaming data from our telescope that's in the lab at UCSD right now. We're doing a cool down with it this week to do some of these tests of this equipment. And I kind of wanted to highlight it because a common thing we have is we have small devices that need to become part of the telescope. And a lot of times we get undergraduate researchers to help us out with that. So we had a graduate student work with an undergraduate to get this pressure gauge up and running so we can understand how we're pulling vacuum on these systems. And the full integration, understanding the component, understanding how to connect it to our computer, and understanding the software we use to program its response into the into our what we call the observatory control system, which is just a software suite we have developed to monitor different aspects of the telescope. And then just because we're here, this is let's go to the last 24 hours. So this is a lot of graduate student work, but often undergraduates have also contributed to just the ability to see, observe, and read out these thermometers at different stages. So you can see that this last day we just cooled down to below 4 Kelvin. Telescope's hanging out 2.5 Kelvin. Then here's the fun one where it shows our base temperatures. So our focal plane is sitting at just below 100 millikelvin with a dilution refrigerator base temperatures of about 40 millikelvin right now. So that's kind of a little more day-to-day in the lab that you'll just have hands-on with these different components, and it's always very satisfying when they actually read out successfully and you can start working with the data to understand what's going on in the system. So yeah, that was kind of the quick overview of what our group does and some of the day-to-day and some of the projects that we've had undergraduate researchers work on. And that's fairly common, and I can speak to that in terms of what people have done in our lab, what kind of research we do, what that looks like more long term. Also, if you're curious, obviously I was once an undergraduate and also did undergraduate research, so I can speak a little bit from my own experience going back through the different stages of my career, both as an undergraduate researcher, as a graduate student working with undergraduate researchers, and now as a postdoc working with graduate and undergraduate researchers. But I'll wrap it up there. Thank you.
Well, thanks everybody. Nice to be here to talk with you. So I'm really glad to be speaking about undergrad research because I think this is a really important part of, understanding what it's like to work in a career in physics or astrophysics or any number of fields. And undergrad research was really important for my career path as well. So I'm happy to give an overview of what my group works on and what undergrad research looks like for us. And then at the end, I have a few just kind of general slides of advice about finding undergrad research projects and how to go about that. So please feel free to interrupt at any point here. Ask a question or ask me to explain something more that's on the slide. So just to start, I'm a professor in the physics department. I've been here for about 5 years. My research is focused on the interstellar medium and star formation in nearby galaxies. And so that means I get to use very beautiful images like this one, which is an image made by the Hubble Space Telescope looking at this nearby galaxy many of you may be familiar with. It's called the Whirlpool Galaxy, or M51. And what you see here kind of encompasses a lot of the things that I'm interested in, although I look at them from many different wavelengths, not just optical, which is the wavelength band that this image is made from. So here we've got a beautiful spiral galaxy. You can see there's it's called a grand design spiral in this case because it's got two kind of really quite perfect spiral arms. All along those, you see these little red patches, which are regions where the gas has been ionized by very young, massive, hot stars that have formed. And they are kind of all over, but predominantly concentrated in the spiral arms of the galaxy. And then you can also see here the light, you can see starlight, you can see some of it is redder or bluer than other places, and this is giving us some indication of the age. But it's also really revealing where there's dust. And I think from this image, even not knowing anything about interstellar dust, you could probably clearly identify it, right? You see these features all along the spiral arm that are, the light coming from those regions is a bit redder than everywhere else. And I'm not talking about the very red blobs, which are ionized hydrogen, but this dusty lanes throughout the galaxy. And that's showing us where there is interstellar gas and dust in M51. And so the questions I'm interested in answering are about how galaxies organize their interstellar medium into clouds that are dense and cold enough to collapse to form new stars. And I'm also very interested in how dust plays a role in that process. So just to give you an idea of where those dense cold clouds are, you get a first idea from just looking at these dust lanes, but we can also observe these galaxies at many other wavelengths. And one of those is in the millimeter part of the spectrum, where we trace cold gas that is associated with something we call molecular clouds. And those are dense regions of the interstellar medium where within the molecular clouds, individual clumps collapse to form new stars. And so this is a survey of M51 done with a telescope in a telescope array in France, the Plateau de Bure interferometer, and this is mapping where all the molecular clouds are. So a lot of what my research day to day is about is observing nearby galaxies in a number of different wavelength bands to trace where the interstellar gas is. And it comes in two basic form, or two general forms that I'm mainly interested in. So this is neutral, just atomic hydrogen, which we trace in the radio part of the spectrum using the 21 centimeter emission line from hydrogen. And these are a series of maps of some nearby galaxies at 21 centimeters. So you can see where all the atomic gas is. Then there's the molecular gas, and these are the same galaxies, so you can jump back and forth to see the differences. And this is where all their molecular gas is. This was a survey I worked on as a postdoc, and it's called Heracles. We used a telescope in Spain called it's the 30-meter telescope at Pico Gaeta. I can't remember the name of the mountain. Anyway, lovely telescope. And we use that to map out where all the molecular gas was in these galaxies. And then we can also map where star formation is happening. And we can see that both from where there's very hot dust. So this is when the interstellar dust is exposed to the radiation produced by young massive stars, it can get very hot, and that produces a lot of emission in the mid-infrared part of the spectrum. So this is maps of galaxies at 24 microns. We can also see either by the ionized gas or by directly looking at ultraviolet light from young stars where all the star formation is happening. So here you see a bunch of UV images of these same galaxies. So just going back and forth, right, we can see where there's gas, where there's star formation, how we trace these things and compare, you know, within these maps, what's happening in the galaxies. And just to clarify, right, we're going here from 21 centimeter wavelengths through millimeter wavelengths through infrared. So this is 24 microns. And then this is ultraviolet. So this is something around 2000 angstroms. So what that means is that we had to use 4 extremely different telescopes in order to get all of these images. And so a lot of the kind of technical work that I do and people in my group do are working with these observations of galaxies from many different telescopes and combining that information to measure properties of the gas and star formation and dust in these galaxies. So so I've talked mostly about gas and star formation, but my true love and where I spend most of my time is thinking about interstellar dust. And interstellar dust is actually critical to all of the physics that just made what I showed you work. So interstellar dust, first off, is in basically the controlling factor in the thermal state of the gas in galaxies. And that's because the temperature of interstellar gas is set by basically the ejection of electrons from dust grains when they absorb photons produced by massive stars. So those photoelectrons deposit their kind of excess energy after they're kicked out of a dust grain into the gas. And that's primarily what heats it up for most of the gas in a galaxy. So the understanding how that works is a really interesting topic, because the efficiency with which you can eject electrons off of a dust grain after you've absorbed a photon depends on all kinds of interesting properties of the dust itself. And so if we wanted to know how this process functions in a galaxy, we really have to, in detail, understand the dust. Dust is also critical because in the process of actually getting parts of molecular clouds to collapse and form new stars, you have to have blocked the existing radiation coming from other nearby stars in order to allow those dense regions to cool off, because a huge part of the process of getting something to collapse is allowing gravity to win over thermal pressure that exists in the gas. And so you have to get it quite cool in order for this to work. And if you're constantly being bombarded with UV photons from elsewhere, it's really hard to cool off to the degree that's necessary. So dust is really important because it shields the molecular gas from the radiation from all these other stars. And the ways in which it does that are also highly dependent on the properties of the dust. So how much of it there is, what size grains there are, what they're made of. So understanding this aspect of dust is also really important to understand star formation. And then once the stars have actually formed in molecular clouds, they then go on to heat up all the dust in their surroundings, because the same exact thing that's causing dust to be good at blocking light and protecting clouds is that it absorbs a lot of these UV photons, and in doing that, it heats up. And so when we look at the infrared emission from dust, we can see places where it's unusually hot compared to the surroundings, and those are spots usually where new stars have formed, and the dust in their vicinity is just exposed to a lot of UV radiation that it's absorbing and causing the grains to heat up. So on the flip side of this shielding molecules thing is that dust radiation itself, so the infrared emission from dust, lets us trace where star formation is happening. So it can be very useful for, like I showed in one of those series of panels of multiple galaxies, using the mid-infrared emission from dust really lets us see where star formation is occurring. This is very useful. So to try to, I just thought I'd give kind of an overview of the directions that my research group is currently working in, and then tell you a bit about some of the projects that undergrads are doing within that. So there's kind of three main efforts that I'm thinking about these days. So the first and sort of the primary one in many aspects is understanding the life cycle of dust in galaxies. So we've already explained, why dust is so important. And the point here is that, we can study dust in the Milky Way, which is really nice because we're sitting in the middle of it and we can learn a lot about dust from very detailed observations of the nearby parts of our galaxy. But if you are interested in general in how star formation works in galaxies, then you have to expand beyond the Milky Way, because if you think about the history of star formation in the universe, most of it happened in a galaxy that was quite different from the Milky Way. It had fewer generations of stars. There are fewer heavy elements produced that are what make up interstellar dust grains. So one of my main things I think about is trying to understand dust in galaxies that are quite different from the Milky Way, particularly in the sense of having less of the heavy elements available that make dust, and how that changes its properties and how it influences the interstellar medium. Then another thing that I think about quite a bit is trying to understand how gas forms molecular clouds and how much of the gas gets allowed to be in a molecular form, given the physics of the interstellar medium, and how that changes from galaxy to galaxy. And then finally, trying to understand how efficiently, once you've got these molecular clouds, you can turn those into stars. And so this kind of ties together the whole idea of understanding star formation in galaxies. So we'll start with the first one. So the life cycle of dust is actually really pretty fascinating. So, and we don't understand it nearly as well as you might think we should. So trying to work on fixing that. So dust can form in a couple of different ways. And there's really two where we've had pretty direct observations of dust forming in this way. So when a star that's around the mass of the sun, or maybe slightly more massive, but not massive enough to become a supernova, once it ends its life cycle on the main sequence, which is when it runs out of hydrogen fuel for fusion in its core, goes through a series of changes where it goes up and becomes a red giant star, and then later on something called an asymptotic giant branch star. And over the course of that process, eventually this star gets very large and kind of loses hold of its atmosphere as it evolves. And there can be these winds and shells of material that get kind of ejected in this process. And those are actually what often form, maybe you've seen something called a planetary nebula. These are the kind of remnants of the atmosphere of a star that's evolved off of the main sequence. And the actual core of the star goes on to become a white dwarf, which is what you see in this little loop here. But in the process of losing its atmosphere, it actually produces a whole bunch of dust. And so this is a really cool process. You can observe it in some atmospheres of AGB stars. So we know some dust forms that way. The other thing we know is that some dust forms in supernova. So when a star, a more massive star ends its life, it actually undergoes a supernova explosion. And in that process, you end up producing a huge amount of heavy elements that are exactly what you need to form dust. And at a certain stage in the development of a supernova remnant, there's a point where it's very efficient to create dust. And so some dust is coming from these type of objects. However, the same supernova actually go on then and destroy dust that already exists in the galaxy. So that may kind of negate whatever they just formed. And when we try to understand all of this together, it turns out we're missing something. And what people think in general, and there's good evidence for, is that some dust has to be just growing in the interstellar medium itself, most likely in dense regions of the interstellar medium where different atoms of heavy elements can meet up with existing dust grains and get attached and kind of, increase the overall mass of the dust. So part of what we try to do is observe various parts of this life cycle in effect and try to characterize their importance. And in particular, one of the things we've been very interested in my group is trying to understand ISM dust growth. So there's, and we've also looked into quite a bit about dust destruction, especially very small dust grains. And speaking of those small dust grains, those are my absolute favorite sort of dust. And there's a type of small dust grain, or you can even call it a large molecule if you'd like, that's made out of carbon, and they are arranged in these carbon rings with hydrogens attached on the outside. We call these polycyclic aromatic hydrocarbons. And these are really cool because since they're very small, they still produce kind of emission features like you would for molecules. And in particular, in the mid-infrared part of the spectrum, there are these vibrational bands of the skeleton of the molecule that show up as these sharp features you can see in the plot here. So these are basically when a polycyclic aromatic hydrocarbon, or PA, absorbs a photon, a UV photon. The way it gets rid of that energy is by vibrating in various different ways and producing photons that are at characteristic wavelengths related to the type of bond that is vibrating. So these grains are actually really cool because the other thing that's important about them is that in addition to actually revealing their presence quite directly with these vibrational bands, it's very easy to eject electrons off of them. So they are critical for understanding the process of heating the interstellar medium. So my group spends a lot of time thinking about PAWs and how much of them there are and how we map them and what destroys them and what forms them and all kinds of stuff. So this is a big focus. And the other kind of, I guess, key aspect of our study of dust is that we are focusing on nearby galaxies. Like this one, this is the Small Magellanic Cloud, observed with the Spitzer Space Telescope. And the reason we look to nearby galaxies is because, you know, aside from what we can do in the Milky Way, when we look at really nearby things, we have the benefit of an outside perspective. Like we're seeing basically the entire galaxy in this image right here. It's a weird galaxy. It's a dwarf galaxy that's interacting with its neighbor, the Large Magellanic Cloud. So it doesn't look particularly orderly like some of the other galaxies we've seen in this talk, but it's a very cool object. And since it's pretty close by, we can actually get really high detail images like you see here that let us study exactly what's happening to the dust in which spot, right? So this is really useful for trying to understand interstellar dust. And moving slightly further away than the Small Magellanic Cloud, we use telescopes. So this is observations from both the Spitzer Space Telescope and the Herschel Space Telescope, looking at nearby galaxies and making maps of where all the dust is and what its properties are. And then, you know, another thing we try to understand is the relationship between how much dust there is and what the kind of raw ingredients you need to make it are. So that includes the heavy element abundance. So that's what you see in the plot on the right. This is the amount of oxygen you have as a function of radius in this galaxy. It's oxygen relative to overall amount of hydrogen. And we can compare the heavy element abundance with how much dust we observe. Sorry. So just further in that direction, we also have been looking at nearby galaxies like the Small Magellanic Cloud using the Hubble Space Telescope to map out, not in emission, but in blocking light, so in extinction, where all the dust is. And we can actually see that in this image. I think if you kind of look at this is a bunch of stars in the Small Magellanic Cloud. And there are some places where you can see that the stars are on average redder than in the rest of the map. And that is because they are behind a bunch of dust, and we can see the change in the color that is introduced by dust blocking the light at certain wavelengths from getting to us from these stars. So the kind of summary of a lot of research efforts is that, you know, what we do is really combine multi-wavelength data for nearby galaxies to try to understand all of these aspects of star formation, dust, interstellar gas. So that's probably my favorite part of this kind of research is being able to use observations from many different telescopes, some of which we can go to, like the IRAM 30 meter here. That was the telescope I went to a lot as a postdoc. Some of which we definitely can't go to because they're in space. And we get to observe galaxies with all of these and combine this information. And one of the really cool projects that I'm excited about at the moment is a survey we call FANGS. So this is physics at high angular resolution in nearby galaxies. Astronomers are really attached to acronyms. I did not come up with this, but it's you know, it's how it goes. Anyway, what we're doing is observing nearby galaxies using the Atacama Large Millimeter Array, which is one of the most powerful interferometers, well, maybe arguably the most powerful interferometer in existence. So this is around 60 telescopes that are located in the desert in Chile, actually very close by to what you just, the observatories you heard about from Nick. So this operates at millimeter wavelengths, and with it, we can map out where in galaxies you have gas, and molecular gas in particular, which is going to collapse and form stars. So I'm just going to skip ahead. I have a bunch of slides here. So I wanted to tell you about some of the projects that undergrads have done in my group. So this was a project led by Bethany Ludwig, who was an undergrad here a few years ago. She's now a grad student at the University of Toronto. So she looked into a core collapse supernova remnant in the Small Magellanic Cloud and used Herschel observations, the Herschel Space Telescope, to find out about how much dust was made in this supernova explosion. And the interesting result that Bethany came to was that before we had Herschel observations, we thought that this supernova had only made a tiny bit of dust, like 1,000th of a solar mass worth of dust. But Bethany found out that in fact, the dust was just really cold and we couldn't see it adequately with the previous telescope observations. And in fact, there's something more like 1/10 of a solar mass worth of dust in this object, which is quite a lot actually. So this was an exciting result, trying to understand how much dust supernova make. I have another undergrad who has been looking at the emission from PAWS and trying to use that as a tracer of where star formation is happening in galaxies. And this is really exciting because actually just about a week ago, Corey, who was a former undergrad here, just submitted his paper for publication. So we're waiting to get back the response on that from the peer review. And so this is very proud of this. So this is one of the first undergrads I've worked with who's fully written a research paper and submitted it for publication. So I'm really proud. And then currently I'm working with Megan Lee, who may or may not be on this call. And she is using a big data set of imaging in the mid-infrared to search for the presence of active galactic nuclei in nearby galaxies. This is just, we're in the early stages of this project, but Megan's already identified, as you can see in this plot, using the colors of the galaxies in the mid-infrared, a number of candidates for objects that might have an active galactic nucleus. And at least one of them is something that's really interesting. And we've only just started doing this, so I'm really pleased with how this project is going. And if Megan's online, she can probably tell you more about that at some point, maybe at the end of this presentation. So with that, I just wanted to maybe just give a few thoughts on undergrad research. You know, I know it's it can be a little bit intimidating, maybe trying to find a project. And so I had just a bit of advice on how to go about that. So there's, just to start, you know, it's really great you guys are doing this, like having different people present. And I think you can already tell, maybe just even from what Nick and I have mentioned, that there's a variety of different ways to do undergrad research. So building an instrument, it could be working on theory problems, it could be analyzing data from a telescope, could be with a single professor, it could be with a group, all kinds of things are possible. I had just a bit of advice about how to go about finding a project. So the first step is really to sort out what you are interested in particularly. So which type of research do you want to do, and have some idea of like why that's what you're interested in. So when you talk to the faculty, you can tell them that. And then, you know, go through the department web pages to identify people who work in that area, and reach out to them to ask what kind of skills are important for a project to work on with them. And some of them may say, you know, no skills, like we'll teach you what you need to know. Some of them may say, you know, it would be great if you could program in Python before you join the lab, or if you could, you know, learn this sort of technique or that sort of thing. So if you have the skills that are necessary, or, you know, if they say there's nothing, no kind of prerequisites or whatever, you can write back and express interest in working on that project. And then otherwise you can work on developing the kind of skills that are necessary to approach them about a project. So some of those that might be useful are being able to do some coding, so a general purpose coding language, and Python is usually a good option there. Maybe that you should maybe put some effort into reading scientific literature, and potentially one of the people you're interested in working with might be able to suggest some readings to start working in that direction. Other things that could be useful, being able to keep a lab notebook, writing down enough information about your work to be reproducible and keep track of things, and then potentially giving presentations and doing some scientific writing. So sorry, I know I'm like at the end of my half hour, but just a few pieces of advice about approaching faculty members. So you can, first off, web stalk their research group. So figure out what they're working on, look at their recent publications, look into what they're posted on the physics department research page. You might be able to try to read one of their publications. Obviously, it's not expected that you'll be able to understand everything immediately, because these are publications for technical in the literature, and this is just to get a basic idea of what they're doing. And then writing to the professor and asking to meet. So if you've had some time to think about, what kind of research they're doing and why you're interested in working on that, then that makes a big step towards them being like, oh, this person is, really serious and interested and has already put in a little bit of effort to understand what we're doing and how they might be a part of it. So, and then, don't be discouraged if not everyone can respond positively to your request. There's people are doing different things at different times, and sometimes it's a okay time to take on students, and sometimes it's not. Sometimes, there's grant proposals due right that week you wrote. There's a lot of faculty too, so you can also reach out to other people as well and try to locate someone to work with. So I think that was all I had.